So, hello everyone, welcome to the TCS seminar. This week we have Krystian Gajdzica from this university. Krystian's research is on the border of number theory and combinatorics, and he will tell us about log-concavity property in the theory of partitions.
Thank you very much for the introduction, and thank you very much for coming. Today I would like to talk a little bit about my research, which I have been investigating during my PhD studies, and I'm still continuing it now. And it is more or less related to the theory of partitions. So at the beginning, let me recall a definition of partition, and then we will go into the log-concavity property. So by a partition of a non-negative integer n, we mean any sequence of positive integers such that the sum of its elements are equal to n, and we assume that the elements in the sequence are in non-increasing order. This is a difference between partitions and compositions, where the order of summands play the role. And with this definition, we can introduce the well-known partition function, which was introduced by Euler in the 18th century, and which is a quite complicated function, as we will see soon. So in particular, we have, for instance, 7 partitions of 5 that correspond to the following sequences. But today, I will just say a few words about some results concerning the partition function. I would like to mostly concentrate on some generalization of the partition function. So the first generalization is the so-called plain partition function. So instead of considering sequences, we can consider the arrays. So here we have the sequence of non-increasing numbers. So now we can translate the numbers, the sequence, into arrays, and consider in how many ways you can represent the number, and as in arrays where the where the numbers in rows and in columns are in non-increasing order. So for instance, we will see that if we take 3 for example, then we have the following possibilities. So 3 is just 3. It's also 2 plus 1, but you can now write it in the following way, or just the sum of ones, but we can put them now in the array, so we have the following possibilities. And let us keep it for a while on the blackboard. So this is the definition of the plain partition function and plain partitions. This is the exact definition, and this is the example I just mentioned. But the most important object from my point of view was the so-called A-partition function. So now we would like to fix a set or a multiset of positive integers, which is reasonable. I will describe what does it mean in a few seconds. So we have a fixed multiset or set of positive integers, and now we consider only partitions of n for which the parts belongs, or the elements of the sequence belong to A, and their sum is equal to n. Of course, because some elements from the multiset set may be repeated, we want to distinguish somehow them. We, for instance, can assign unique color to each number of this multiset. And we also need an additional requirement which will tell us that this is in fact a different object than the A composition. So we have an additional assumption that 2 A-partitions are considered the same if they differ only in the order of their parts. And especially as in the case of the partition function, we can define the A-partition function. And now we can take actually any multiset, actually not every multiset, because if we assume that, for instance, a multiset A consists only of ones, and there are infinitely many of ones, then we have infinitely many representations for n, for every n greater or equal than 1. So we have additional assumption that this reasonable means every number j occurs only infinitely many times in A. And now have some examples. So in particular, if we have the set of positive integers, then we obtain the partition function. If we take n but without some multiples of k, then we obtain the so-called k-regular partition function. This is some examples of sets. There is also something like MR partition function, which is the set of consecutive powers of a fixed parameter n. And k-color partition function, where each number j occurs exactly k times in A. And the next example is the plane partition function, which I introduced recently, but it's a little bit different. There is a definition which says that the number of this two-dimensional partition is the same as the number of partition of n into parts that where each number j can occurs in j distinct colors. So it is non-trivial, actually, correspondence between this definition of plane partition and that one, and it was proven by Mahon in 1920s, and it took him 20 years to prove that the bijection between this object and the fifth one from the slide. Okay, and of course we don't need to restrict ourselves only to infinite multisets. We can, for instance, take the following one and the corresponding A-partitions. Well, there are exactly 7 of them for n equals 5. Okay, are there any questions or comments at the moment? Because now I would like to pass to the log-concavity property.
Yes, there is a comment. A question.
Okay.
What methods were used in proving that fifth plane partition function is the same as?
Oh well, it's just via so there's the consideration of generating function to variables generating function, and then maybe you heard about something like RSK correspondence. So it is well known. So this is the correspondence between permutations and Young tableau, which are fulfilled with numbers. Maybe you heard about this. So this is the, for instance, hook length formula. If you heard about, so this is a direct connection between Young tables and RSK. You can use it, and then obtaining the generating function, you will be able to deduce the appropriate correspondence. So the proof can be done combinatorially, actually, of course, with some uses of quite well-developed techniques related to RSK. Okay, great. So what do we have further? So now we have the log-concavity, a log-convexity property. So we say that the sequence of real numbers is log-concave if it fulfills the following inequality. Sometimes the strong inequality is replaced by the weak one. Here we will assume that it is the strong. There is a strong inequality, and the log-convexity is almost the same. The difference that there is an inverse inequality here at point and 0. So there is also another thing related to log-concavity and log-convexity. It's called unimodality. So here we consider a finite sequence. It also can be infinite, but for some reason I assume that it's finite. We say that it's unimodal if there is some point I0 such that the sequence is weakly increasing to that point I0, and after that it is weakly decreasing. And in particular, one can show that if you have a sequence of positive real numbers, then log-concavity in particular implies unimodality. There is a well-known sequence which is log-concave and unimodal. It's the sequence of binomial coefficients. So k equals 0 to unimodal and log-concave. And one can ask, why do we consider such a thing? Why do we care about it? So actually, it turns out that this log-concavity and log-convexity property appear in many different areas. For instance, in the mathematical biology, it counts some biopolymer structures, and in signal processing, the so-called wide nose theory, where there is some equivalent relation between log-concave sequences and nuclear spaces. This. Also, in quantum physics, there is a way to construct coherent discrete nonlinear spectra models. And in probability theory, someone can show that if we would like to have a random variable which is infinitely divisible, then log-concavity property plays the role. Then in algebraic geometry, on the other hand, we have a nice description of acting Lie algebras on cohomology, on some cohomology ring on variety in complex numbers. And in graph theory in particular, it is quite nice because there is a well-known results related to John Hough, who in 2022 was awarded Fields Medal. And in particular, he showed that chromatic polynomials, the coefficient of chromatic polynomials are log-concave, as well as the coefficients of the characteristic polynomials of matrices. But there is also a result to Heyman and Leib, as far as I remember, which is related to matching polynomials and some Gauss distribution. Also, it turns out that log-concavity property appears in some coding theories somehow. Someone can consider Hamming codes, and people use log-concavity property to investigate these codes there as well. But now we would like to go to the main part of this talk, so the log-concavity property for the partition function. So let me call this the definition of the log-concavity as before. And now it turns out that the sequence of the partition function is log-concave for all n greater or equal to 126. It was proved, or rather reproved, in 2015 by Salvo and Pak. Actually, Nicholas proved it many years before, but his work, unfortunately, was forgotten for a few decades, unfortunately. Nevertheless, the result due to Salvo and Pak has initiated wide research related to investigating similar properties for other partition statistics. So in particular, now we have many such results for various partition functions. And what I wanted to do during my PhD, I wanted to investigate that issue in the context of a partition function, but when A is a finite multiset. Because here, as we see, all of these theorems are related to one sometimes special case of a partition function. So maybe we are able to do something in general. And it turns out that indeed we are, but before we do that, let us take a look on an example. So for instance, if we take the most natural example, so now we consider a partition function, so the set nk, which is the set of the first k positive integers, then one can easily show that the number of partition of n into parts 1 and 2 is just the following number. It's very easy. If we consider the numbers 1, 2, and 3, then this is the following function. This bracket means that it is the rounded to the nearest integer. So in particular, one need to show that this is never half of the integer. It's not very difficult. And there are many more such formulas for the set nk. In particular, Sils and Zeileberg computed all of this function up to k equals 60 as per se. So now we can take the following function, which will be description when our nk partition function is log-concave. So if it is positive, then we have the log-concavity property. If it's negative, then we have log-convexity. And let us consider this function above. So in particular, if k is smaller or equal than 4, then it turns out that the graphs look like that. So we have infinitely many numbers for which the partition function, because the partition function is positive, as well as infinitely many points for which it is negative. However, if we assume that k is at least 5, then it turns out logically that it will be always positive for sufficiently large values of n. So, and it is so, actually, more or less, if we have these numbers 1, 2, 3, 4, 5, then we get anything to our set nk, and we still will have the log-concavity property. So let me at the beginning say a few words about the theorem I was able to derive. So here we have a finite multiset of positive integers, and if k is between 2, if k is either 3 or 2, then we need to require that a1 is equal to a2 is equal to a3 equals 1. But if k is at least 4, then we have a nice description. Namely, we need to require that every k minus 2 element multi-subset B of A is coprime. If that is the case, then we have the log-concavity property for all large values of A. And what is interesting here is that it is the complete description. There is no any other A-partition function when A is a finite multiset for which this inequality holds. So it's if and only if, actually, for finite case. But we can go even further, namely we can try to add some factor on the right-hand side, and it turns out that still we are able to obtain a little bit stronger theorem stating that the following inequality is also true. So of course, it's fine that it is quite nice that it describes all A-partition function for which this inequality holds, but the problem is this number is very large and is in fact very, very not optimal, let's say. Okay, so maybe let me say a few words about the proof. So why do we able to deal with the log-concavity property when A is a finite multiset? Okay. Because we have a good understanding of the asymptotics of the behavior of the corresponding A-partition function. In particular, Bell in 1943 showed that A-partition function behaves like a polynomial. It's not a polynomial, it's a quasi-polynomial of degree k minus 1. So the quasi-polynomial means that the coefficients of this expression depend on the residue class of n modulo the least common multiple of A. However, it is a general result, so maybe if we assume something more about these numbers a1 up to ak, then we will be able to say something more about our A-partition function. And in fact, it's true. Namely, for instance, if we assume that the greatest common divisor of a1 up to ak is 1, then it turns out that the leading coefficient is independent of the residue class of n modulo the least common multiple of A. We can go even further, namely, there is a nice result in the term Quits. Also, this was proven by Israelov and Beck, but Amquist gave quite nice characterization, namely if we have this multiset A, and we have this assumption that every J multisubset B of A is coprime, then we have the following expression for the A-partition function. We don't need to care about this expression. The most important thing is that it says that if every k minus 1 multisubset is coprime, then not only the leading coefficient is independent of the residue class, but also the second one is also independent. If we assume, on the other hand, that every k minus 2 multisubset is coprime, then not only the first one, the second one, and the third one, all of them are independent of the residue class of n modulo the least common multiple of A. So now the idea is quite easy. Namely, we just want to... okay, sorry. There is another thing. This is the definition of the symmetric polynomials appearing in the sum. Not very important. Actually, this family of symmetric polynomials also appears somewhere in topology, but I don't remember now where exactly. So sorry for that. And the idea, as I mentioned now, is just to bound the A-partition function from below and from above. by the expression of the following form. So if we have that the leading coefficient is dependent, so the greatest common divisor of A is equal to 1, if we assume only this thing, then we can try to find some number bk such that the following inequalities hold. And then we just take the lower bound for PAN squared, so this one to squared, and the upper bound for PAN plus 1 times PAN minus 1, and it turns out that it is negative, unfortunately. However, if we go a step further, then we still unfortunately obtain that it is negative. But if in the next step we obtain that this negativity will be replaced by positivity for large values of n. So the question is, how can we find these numbers ck or bk? And the idea is to use another description of the A-partition function, which is also quite technical, namely, we have the following description of A-partition function in terms of the unsigned Stirling numbers of the first kind. So it's actually not very beautiful, but somehow one can derive from it the upper bound for the appropriate bounds ck or bk from the previous slide. So that's the idea. Now we can recall our theorem and see that the following examples. So, for instance, now if we take any multiset, so let us say that this multiset begins like this. So there are 5 twos and 3 threes at the beginning. AK is defined in the following way. Then, when k is smaller or equal to 7, we don't have the log-concavity property. But if k is at least 8, then we will obtain the log-concavity property. And moreover, now we just use all of these numbers, and in fact, we don't need to care about the next numbers, because whatever we add, we'll obtain the log-concavity property as well. Are there any questions or comments? If not, then we can proceed. Then we can pass to the next problem, which is slightly easier, but also nice, namely to the Bassenrat-Ono inequality. So instead of considering the log-concavity property, one can try to deal with the following problem. So it turns out that the partition function fulfills the following inequality. It was proved by Bassenrat and Ono in 2016. The original proof was done in analytic manner. So all the authors, Bassenrat and Ono, use the lemma type estimation, which follows from Rademacher formula for the partition function. But it's nice that we also have the combinatorial proof that were Nazi, Jagiellonian, and Munagi. And there is also a proof by induction by Heim and Neuhauser. Actually, let me sketch the proof in an analytic manner. So the authors, Bassenrat and Ono, used the theorem of lemma, which says that the partition function is equal to the following expression, from which one can derive the lower and the upper bound for partition function of the following form. And now the approach is as before, so we just want to bound PA times PB by the lower bound and the P of A plus B by the upper bound, and check when the appropriate inequality holds. If we do so, then we are able to deduce the theorem from the previous slide. It also turns out that we have many similar results for other partition statistics. So here is the case of the k-colored partition function. Also, there are some results for k-regular partition function for partitions with rank in an arbitrary residue class modulo T. So the rank of a partition is the so for a partition, it is the largest part minus the number of parts appearing in the partition. And for many more partition statistics, we have many similar results. So in the case of the A-partition function, we have a natural situation, namely, it's enough to assume that the greatest common divisor of A is equal to 1. If that is the case, then we have this inequality. And here also we have this not very beautiful number as a lower bound for A and B, which follows from this approach I mentioned before. But the most important fact is that, and it is actually easy to see here, that this is the condition, this is the necessary condition, but also it's sufficient condition. It's sufficient condition, but also the necessary. So we have the if and only if here. Because if it is not the case, if the greatest common divisor is not equal to 1, then there are infinitely many numbers for which the A-partition function is equal to 0, because we have some number. We can only express the numbers which are the multiples of the greatest common divisor. If the greatest common divisor is greater than 1, then there are infinitely many numbers which cannot be expressed as a sum of numbers from A. So here is the problem, which is, in my view, quite interesting. So now let us assume that A is finite or infinite multiset. Then we have so the question is whether we have the Poisson-Ono inequality for the A-partition function for all sufficient large values of A and B. Is it true that it is if and only if the cardinality of A is at least 2 and the greatest common divisor of A is equal to 1? So in the case when A is infinite, it means that we have a finite multi-subset of A for which we have this condition. Good. So as I mentioned, that there are also proofs in a combinatorial manner. So let me present one. Actually, it is not directly related to the Poisson-Ono inequality, but it's the criterion for the A-partition function when A is a finite, when A is an infinite, actually set of positive integers. Also, it may be finite, but we have the complete description for finite multisets. So let us consider now infinite A. We assume that A is of the following form. We have some additional requirements. For instance, that the difference between two consecutive numbers is at least A3 for every R greater or equal than 3, and the assumption that A3 is at least 2 times A2. If that is the case, and if we additionally assume that the Poisson-Ono inequality holds for small values of B and Z between 2A3 and 2A3 plus 2A2 minus 1, then we are able to obtain the Poisson-Ono inequality for all values of B and C. And the proof is quite easy in reasoning. The reasoning is quite easy. Namely, we want to consider the number of A-partitions of A plus B. So either we have A2 as a part in this partition. If that is the case, then we can subtract it from A plus B, obtaining the number of partitions of A plus B minus A2. If we don't use the A2 as a part, then we have the number of A partitions without A2 of A plus B. And now we would like to apply induction hypothesis to the first term. And to the second one, we would like to show some combinatorial argument showing that this number is smaller or equal than that one. If that is the case, then we can take PA of B in front of the brackets and use the same trick as in the first line to rewrite it as the following. So now the idea is the question is how to prove the following inequality. So the most natural is just to build appropriate injection from the set of partition counting on the right-hand side to the Cartesian product of the partitions counting on the left-hand side. So how can we do that? I will not go into details, but only sketch the idea. So we take a partition from the set of partition of V and Z, where A2 does not occur as a part. So all of them are of the following form, where lambda 1 up to lambda t are numbers greater or equal than A3, and there are some ones at the end. Then we want to obtain something, and we want to have something from the Cartesian product. We define additional parameter I, which is defined as the maximum J, such that this number is still greater than or equal than Z. And for this parameter, we take the part corresponding to it, write it as x plus y. It turns out that x plus lambda I plus 1 up to lambda t plus s is equal to z, and lambda 1 up to lambda I minus 1 plus y is equal to w. And from our assumption, it follows that x must be at least 1 and y is greater or equal to 0. So now let us omit maybe slide, but the thing is that we need to be careful here because we need to build injection. So the thing is that we need to check whether it is well defined, whether it is also injective. So in every step, we need to compare our mapping to the previous one, checking whether we have the injection and well defined. Okay, so this is the idea of the proof, and now from what can we do with our criterion? Namely, we can consider, for instance, the M-ary partition function. So this is the case when A is a set of consecutive powers of M, and we can obtain the complete description of the Bassenrod-Ono inequality. Namely, one can show that it holds for all V and Z greater or equal than Nm, where Nm depends on the value of M. Also, there is one application of the Bassenrod-Ono inequality in the theory of partitions. Namely, we can consider the so-called extended M-ary partition function. So for the M-ary partition function lambda j, we can define the extended M-ary partition function, which is the product over these parts of the values of M-ary partition function on them. And now we are able to check when the maximal value of this function is, where the maximal value of this function is attained. In particular, if we fix n, then it turns out that for all m greater or equal than 3, we have that the maximal product is attained at the partition of the following form. For m equals 2, we have an exception because here we have many two partitions for which the maximal product is attained. Great. So at the moment, as I said, we don't have the asymptotic estimates for a partition function where A is an infinite multiset, where A is a random or arbitrary infinite multiset of positive integers. But let us assume that we have. So let us assume that we have a function which can be bounded from below and from above by the following expressions. And if we add some additional requirements on this function C1, C2, and f of n, then we are able to deduce the Bassenrod-Ono inequality. So, for instance, we need to have the following condition, which is quite. So, of course, without loss of generality, we may always assume that A is at least B. So we have the following assumption. The additional one for C1 and C2 takes the following form, and also we need to have a connection between the function GH and C1. If that is the case, then we are able to obtain the Bassenrod-Ono inequality for all A and B greater or equal than the maximum all of these parameters appearing in these conditions. So here we assume that we have the estimates for our function. So this is the most important thing, because for many A-partition function where A is infinite, we don't have the explicit description of its growth. And using it, for instance, for the partition function, and if we take advantage of the estimates from the Bassenrod-Ono paper, then we obtain the appropriate inequality for all A and B greater or equal than 2. So what about the log-concavity property? We can try to do the same. Here we have additional assumption that there is a function h of n which satisfies for the following inequality. Also, there is some. So there's expression C2 n plus 1, C2 n minus 1 over C1 squared is smaller than e to the power h of n. And these two conditions are enough to deduce the log-concavity property for our function f. And once again, going back to our partition function, if we take the appropriate estimates, so for instance, one can take this one. It also follows from one of the paper, but I don't remember now from which one. Actually, it was the one related to some more sophisticated problem than log-concavity, but maybe we will have some time at the end to talk about it a little bit more. Then we are able to deduce this property for all n greater than 94, and for smaller n, we can just look at them one by one and check it on hands. Great. So now maybe on this, to finish this part, let me say also a few things about the connection between log-concavity and Poisson-Ono type inequality. So usually, from log-concavity implies the Poisson-Ono, but we need to be careful. So, for instance, if we have the log-concavity from some point, and we have additional requirement that this Poisson-Ono inequality for n and 0 holds, then we are able to deduce the Poisson-Ono inequality for all a and b greater or equal than this n parameter and 0. So in particular, if we knew that this holds, then we would be able to deduce that that partition function fulfills the Poisson-Ono inequality for all a and b greater or equal than 26. We can go further, namely we can assume that there is the function f satisfies the log-concavity property for all n greater or equal than 1, and it is greater or equal than 1 for n equals 0. If that is the case, then we have the log-concavity property for all a and b. But we need to also be careful here because we can try to apply it for the partition function, and it turns out that, okay, so it's log-concave for p of 26, it's the first point, and then we have always log-concavity property. It is strictly greater than 1. So we can take the sequence p of n plus 26. It satisfies the Poisson-Ono inequality for all a and b, but this Poisson-Ono inequality does not correspond to the original one, because on the left-hand side, so we will have p of a plus 26 times p of p plus 26 is greater than p of a plus b plus 26, but we need to have 52 on the other side. Good, and another example shows that if we take a sequence of even Fibonacci numbers, so Fibonacci numbers with even indices, then by Cassini identity, we have that the difference between the following difference corresponding to the log-concavity property is equal to 1, but we don't have the Poisson-Ono inequality for n a and b greater or equal than 1. So this requirement that f of 0 is greater or equal than 1 plays the role actually. Also, as in the case for the MRA partition function, I told you that it satisfies the Poisson-Ono inequality, but it's not log-concave. And it can be also, one can also check it if we consider n, which is congruent to minus 1 mod n, then we have the following equalities, but Pm of n plus 1 is strictly larger, so for all n of the following form, we don't have the log-concavity property. Good. Are there any questions? Comments for that part? Okay, so now let me go to another problem, which is also quite, maybe this was quite technical, I suppose. Now we also see some generalization of the partition functions. So the generating function for the A-partition function takes the following form. If we take the generating function for the classical partition functions, the following one. Actually, the first Euler proved it in 1748, as far as I remember. The generating function for the plane partition function takes the following form. So as I mentioned at the beginning, the plane partition function corresponds to the two-dimensional partition somehow. So now I can ask, okay, so how does the three-dimensional partition function look like? So is it of the following form or something similar? It turns out that it's not true, and in fact nobody knows, because it's very complicated. and a lot of people suspect that there is no easy generating function for that function. So one can ask, okay, so you would like to have some extension of the partition function, but something that have a nice combinatorial interpretation. We have some kind of that object, and it turns out that in fact we have, namely, we need to go to permutations. So let us assume that L and n are greater or equal to a positive integer, that is greater to 2. And we define the set of L tuples of pairwise commuting permutations. If we define the number, the cardinality of this set divided by n factorial, then we also need something. So this is actually not very important. The most important thing is that the generating function for this number is of the following form. And if we take L equals 2, then we obtain the partition function. So the number of partitions corresponds directly to the number of 2 tuples of pairwise commuting permutations. But here we have also the natural generalization of this function, because we have the algebraic combinatoric interpretations of this coefficient L over L of N. So now, instead of considering the log-concavity for all sufficiently large values of n, let us fix n, check the log-concavity for this n, but we can now vary with L. Goes with L to infinity, and check what we will get. So we have this, for instance, for this family NL. We have the following description. It turns out it's some kind of magic, I suppose, that we have mod free behavior. So it turns out that whenever n is 0 mod free, then it's log-concave. But if n is not congruent to free, then we have the log-convex property for large values of L. Similarly, if we take the extension as in the case of the plane partition function and this one, so instead of this function GL from the previous slide, we take n to the power d minus 1, then we obtain a very similar description. So we have that. So here's the figure which shows when the function PD of n is log-convex. So blue points means that it's log-convex there. So it's log-convex for all n that are non-congruent to 0 mod free. So we can try to generalize it somehow, because maybe in the future somebody will discover another nice generalization of maybe not partition function, but of A-partition function or something else. So here we have a sequence of function fl, which goes from positive integers to positive integers, two functions psi and phi, such that the sequence fl of n is bounded from below and from above by the following expressions. And the difference between psi of L and phi of L is not very large, which is just at most some constant. And also we have additional requirement that this function, both of these functions, psi and phi, goes to infinity as L grows. So actually we just want to generalize the previous theorem for many more generalization of the partition functions. So what do we get? So now we can take our set of positive integers for which we have 1 as a part of this set. And it turns, if we define the generating function of the following form, so these numbers are defined by the generating function of the following form, then we are able to say something about the log-concavity and log-convexity as well. And it turns out that these properties mainly depend on the following number, capital M A of n, which is the maximum. So in fact, we consider all A partitions of n. We take the product of, for each partition, we take a product of its parts and check for which partition we have the largest product. This is the description of this capital M of U. And it turns out that the log-concavity as well as log-convexity heavily depends on that number. Namely, if we define the quotient which is directly related to the log-concavity property, it turns out that if this quotient is larger than 1, then we have the log-concavity property. If it is smaller than 1, then we have log-convexity property. And the natural question is, of course, what do we have if this quotient is equal to 1? Then the situation is tricky. We need additional result, which is unfortunately not complete as well. But okay, let me say a few words about it. So now we assume that this quotient is equal to 1. We additionally require that the maximal product for n is larger than the maximal product for n minus the product for n minus 1. And okay, this is the assumption for the quotient from the previous slide. And we need to also require that this maximal values, maximal products, are attained by the unique A-partition. If that is the case, and we have the asymptotic, very similar asymptotic behavior of this function g of L from previous slides, then it turns out that very similar phenomena holds. So if we have some additional function qa of n, for which the following is greater than 1, then it is log-concave. Otherwise, if it's not smaller than 1, then we have the log-convexity. For if it's equal to 1, we don't know actually at the moment. And this function is the number of all compositions. So as I mentioned at the beginning of my talk, the difference between composition and partition is that we care about the order of summands in sums. So this is the number of composition for which the maximum value is attained, and this is divided by the length of this composition. So this k factorial means that this composition for which the maximum value is attained is of length k, so it has k parts. So what does follow from this theorem? So the first one is that if we assume that now A is a set such that 1, 2, and 3 belong to A, then we have that it's log-concave for all L if n is 0 mod 3. It is log-convex for n if n is 1 mod 3. And we don't know actually what do we have for n congruent to 2 mod 3. But the most important thing here is, once again, I don't care what do we else have in our set A. We can have anything we want. But this will be true. Of course, yeah, it depends, of course, whether 4 is in our set or not. But we can add, for instance, 700, whatever we like. We will still have this property. But there is a tricky problem with 4, namely if 4 belongs to our set A, then we don't know, and we can have two options, either log-concavity and log-convexity as well. Another thing is that if we take the set A with where 1 and 2 belongs and 3 does not belong there, and then we can have there whatever we like, we will have the log-concavity for all n congruent to 0 mod 2 and log-convexity for odd numbers n. Here is the example. So for instance, if I take as A the set of all numbers without 4 and 8, and all numbers between 8 and 16, then we have from previous slide the log-concavity only for the log-convexity is only for the residue class 1 mod 3, I suppose. Yeah, 1 mod 3. This is the case when 3 does not belong to our set. Then we have this behavior mod 2. And there is also another case. So now we can assume that A is of the following form. So 1 belongs to A. There is some break. Some R belongs to A, and R plus 1 belongs to A. Then we have the log-concavity property for all n that are not congruent to R minus 1 mod R, and log-convexity for this one residue class mod R. So in particular, if we take as A 1, 4, 5, and whatever we like further, then we obtain the figure of the following form. Okay, and here is a very curious problem which I was thinking about last year a little bit. Namely, a lot of these problems, as I mentioned, depends on the maximal product from defined before. But we can try to, for a fixed set A of positive integers, we can try to deal with similar problems. So I give you number n, I give you a set, arbitrary set A of positive integers, and ask you for which A-partition do we have the largest product for that. And it turns out that it heavily depends on this A2 here. If A2, so here it is R, if A2 is greater or equal than 3, we will always obtain mod A2 behavior. Okay, so how much time do I have? Okay, so maybe I will go to some further generalization of the log-concavity property now. I will not go into details. I suppose that it will be enough if I just sketch what can we further do. So the next step is the R log-concavity problem. So now we can consider the sequence defined in the following way. So this curly L hat n just correspond to the log-concavity problem. We can iterate it now. L I of C of n is of the following form. And we can ask, okay, so if we say that if all of these functions are positive for all large values of n, then the sequence Cn is called to be asymptotically R log-concave. So in particular, it's the one log-concave. One log-concavity just corresponds to the log-concavity property. And here we have the result for the partition function. There are also some other results for the over-partition function as well, and for the A-partition we will see now. What does it look like? So here we can use some different stuff, namely the piso-type approximation. There is a nice characterization of the R log-concavity using piso-type approximation of a sequence. Namely, if we have for the log-concavity quotient, we have the piso-type approximation of the following form, then we are able to say something about the asymptotically R log-concavity. We can try to apply this theorem in the case of our function, for our A-partition function, when A is a finite multiset. Actually, it doesn't work. One needs to improve a little bit this theorem. But it may be done, and it turns out that it is, as we probably suspected, that now the R log-concavity happens if and only if every k minus 2R multisubset B of A is co-prime. So in particular, if we have two log-concavity, then we need to require for our plane partition function that, okay, so the multiset corresponding to plane partition function, we need to require that k is at least 11. And it will be always true for k greater or equal than 11, as before. So this is the first thing, and now, at the end, I would like to go to Riemann hypothesis a little bit, but just a little bit, namely, we say that the sequence of real numbers satisfies the second order inequality. It's a weak version of the log-concavity property. We say that it fulfills the third order term inequality if the following is true, and I don't want to write down all of these inequalities, but I will just give you the equivalent statement for these inequalities. Namely, if you consider the Jensen polynomial of degree b and shift n associated with the sequence C, so this is the expression of the following form, then we say that the sequence Ci satisfies the order D Turan inequality at n if this polynomial is hyperbolic, so it means that all of its roots are real numbers. So I mentioned that it's right a little bit connected with the Riemann hypothesis because there is an equivalent statement to the Riemann hypothesis saying that the Xi Riemann function belongs to Laguerre-Polya class. And I won't go into details what the Laguerre-Polya class means, but there is a necessary condition for a function to be in a Laguerre-Polya class. It is that the Taylor series of its coefficients satisfy the Turan inequalities of any higher order Turan inequalities for any D, and for all values. Yeah. So here is the criterion I would like to talk about a little bit. Namely, in 2019, Griffin and Ono give a nice criterion. I also want to go into details, but more or less, this theorem states that the Jensen polynomial from the previous slide can be somehow approximated by some polynomial, which, if you are lucky, is orthogonal polynomial. For instance, it may be Chebyshev polynomial, or it may be Hermite polynomial, or Laguerre polynomial. But about Laguerre polynomial or Hermite polynomials, we know that they have only distinct roots and only real roots. So here is a small deformation which does not influence on the roots of the considered polynomials. So in the case of the A-partition function, when A is a finite, we obtain here the generalized Laguerre polynomials, which only have real roots, distinct real roots. So we can deduce that the Jensen polynomial associated to our A-partition function is in fact hyperbolic. But here we have only a sufficient condition, namely if we have that every k minus d multi-subset B of A is coprime, then we have the order D Turan inequality. So for instance, in our case, if k is at least 7, we obtain the third order Turan inequality for the considered A-partition function. But this theorem is not optimal, in contrast to the previous theorems, namely because we have a counterexample. If we take a multiset A, it is not the best counterexample, but it works. A multiset A which consists of 4 ones and 300, and we consider the fourth Turan inequality, then it turns out, of course, we need to have every k minus 4 multi-subset must be coprime, so every number must be coprime, so it means that every number must be equal to 1, but here we have 300, so it is not true. However, we still have the fourth order Turan inequality for that function. One can show that in fact it's bounded from below by the expression of the following form. Okay, another problem, maybe I will not go into details because only about Laguerre-Polya class and Laguerre inequalities in this case, so it's directly connected to Laguerre-Polya class. Here we have another cases also using the same strategy as before. We have a lot of results related to Laguerre inequalities for various combinatorial sequences. In particular, the most important one is Duet-Wagner from 2022, which states that the partition function satisfies the order D Laguerre inequality for any D. So in the case of the A-partition function, once again, we have a very similar description as in the case of the higher order Turan inequalities, but with the difference that now we require that every k minus 2D multi-subset is coprime. And once again, it is not optimal, it's a sufficient condition. We have that it holds if this true, then we have for large values of n, we have the required property. But once again, we can take our favorite example, consider the second Laguerre inequality and obtain that it does not satisfy the previous assumption, but still we have the second order Laguerre inequality. And that's, I think, everything I wanted to say today. There are some open problems I will mention at the end. So, this is the end. Thank you very much for your attention.